Hello, myself, Professor H.K. Bhandare from Department of First Year Engineering, SND College of Engineering and Research Center, EOLA. I welcome you in video lecture series of Basic Electrical Engineering of First Year Engineering course. So we are today discuss about the DC circuit. In that we analyze the circuits, the circuit analysis. But before the circuit analysis, we'll see what exactly is the circuit analysis. We are analyzing the circuit means what? Simply we are determining the different values or different parameters of the circuits like voltages and currents, either across a certain element or flowing through certain branch. So either we will find out the voltage across certain element or the currents flowing through certain particular branch. And to find out these variables is nothing but the analysis of that particular circuit. So we'll use certain tools to analyze the circuit, and the basic tools used for the analysis of the circuit here is we'll use the Kirchhoff's laws. So before analyzing, let us revise that Kirchhoff's laws. Kirchhoff's has stated two different laws: Kirchhoff's current law and Kirchhoff's voltage law. So what is Kirchhoff's current law? The algebraic sum of the currents leaving a node equal to 0. The algebraic sum of the currents leaving the node equal to 0. That time the IA, whatever the incoming currents are there, they are considered as negative. Now here all are in outgoing currents. So in this case, the algebraic sum of the currents leaving a node is equal to 0. Or in other words, we can define the Kirchhoff's current law as the algebraic sum of the currents entering a node equal to 0. Now here in this example, all currents are entering to the node. So the algebraic sum of all these currents is 0. Now here in this example, the currents are entering and also leaving the node. So in this case, we can define the Kirchhoff's current law as a consequence that the sum of the currents entering a node is equal to the sum of the currents leaving the node. So the summation of the currents entering at the node is equal to summation of the current leaving that node. So that is nothing but your Kirchhoff's current law. So next is Kirchhoff's voltage law. Now what is Kirchhoff's voltage law? So here the algebraic sum of the voltages around each loop is 0. So beginning with one node, add voltages across each branch in the loop. So the summation of the voltage drop minus summation of voltage rises, that is equal to 0, or summation of voltage drop is equal to summation of voltage rises in that particular loop. So the Kirchhoff's voltage law is simply the algebraic sum of the voltages around each loop is always 0. Now let us analyze the circuit. Now here one circuit is given. Two resistors are connected in series here, and their values are 7 ohm and 3 ohm respectively, and they are connected across a 12-volt battery source. Now when the given circuit with sources and resistors having a fixed values, you can use Kirchhoff's two laws and Ohm's law to determine all branch voltages and the currents. Now if I ask you to find out the current flowing to all branches and also the voltage drop across each resistor, and for that we can use Kirchhoff's both the laws as well as we can use the Ohm's law along with that. So let us see the voltage across the 7 ohm resistance or between the terminals A and B is VAB. Voltage across this point B and C, that is this 3 ohm resistance, let us say it is VBC, and this is a 12-volt battery source. So by Ohm's law, VAB is equal to VAB, that is voltage drop across 7 ohm resistance, is current flowing through that into value of the resistance. Value of the resistance is 7 and current is flowing, let us say it is I ampere of current flowing through that resistor. So VAB is equal to 1.7 ohm. Similarly, VBC is equal to I into 3 ohm. So it is I into 7 ohm VAB, and it is I into 3 ohm. That is nothing but your voltage across the BC. or 3 ohm resistor. Now by KVL, we can write that the sum of the EMFs across a loop is always 0, that is VAB plus VBC and minus 12 volt, that should be equal to 0. So put the values of VAB and VBC here. So I will get it I into 7 or 7I plus 3I minus 12 volt is equal to 0. So next equation will get like this. Substituting 1.7 ohm plus I 7I plus 3I minus 12 volt is equal to 0. So here by solving this equation, we will get 7 plus 3, that is 10I minus 12 is equal to 0, means 10I is equal to 12 volt, means I is equal to 12 upon 10, means the current flowing through this circuit is 1.2 ampere. Now here the next example is given. Now solve for the currents through each resistor and the voltage drop across each resistor. So you have to find out the current flowing through the branches, that is I1, I2 and I3. And also you have to find out the voltage drop across the 10 ohm resistance, voltage drop across this 8 ohm resistance, voltage drop across 6 ohm and 4 ohm resistance. So let us begin with this. So using Ohm's law, add polarities and expression for each resistor's voltage. So here across this 10 ohm resistor, current flowing is I1. So according to Ohm's law, the voltage drop across 10 ohm resistance is 10 I1. And we give the polarity, current is flowing in this direction from high potential to low potential. So it is plus and minus. Then next resistor, 6 ohm resistor, voltage drop across the 6 ohm resistor is 6 I3, because I3 current is flowing through this branch and current direction is like this. So it is plus 6 I3. Then voltage drop across 4 ohm resistance is 4 I3. Then voltage drop across 8 ohm resistance is 8 I2, because I2 current is flowing through this 8 ohm resistance and the direction of current is like this, means positive to negative. Now we'll consider the first loop. This is a first loop. Now do apply the first Kirchhoff's voltage law. Apply first the Kirchhoff's voltage law equation for this loop 1. So it is minus 50 volt plus 10 I1 plus 8 I2, that is equal to 0. So we will get this first equation. We encounter or we travels in this loop, first loop, and while traveling through this loop, we comes in contact with the voltage drop across 10 ohm, 8 ohm resistance. Voltage drop across this is 10 I1, it is 8 I2, and sum of all this is equal to 0. So that equation is minus 50 volt plus I1, 10 I1 plus 8 I2 is equal to 0. Our second equation we will get as for this loop, second loop. So it is I2 is equal to I2 into 8, I2 into 8 ohm resistance. So I2 is equal to I3 into 6 plus 4 upon 8, that is 1.25 I3. But this equation, second equation, you will get as minus I2 8 minus I2 8, because we are moving in this direction. So it is against the flow of the current I2. So it is minus voltage drop across this 8 ohm resistor in this slope, because we are opposing in the direction of opposite to the current I2. So it is minus 8 I2 plus 6 I3 plus 4 I3, and that is equal to 0. So this is the second equation. This is your second equation. Or in otherwise we can write that I2 is equal to, this I2 is equal to 8 I2. I2 is equal to I3 into bracket 6 plus 4, I3 common, 6 plus 4 is 10. It is 10 I3 upon 8. It is 1.25 I3. So second equation in short we get as I2 is equal to 1.25 I3. So we now have these three equations in three unknowns. So we can solve for the current through each resistor that are used to find the voltage across each resistor. So since I1 minus I2 minus I3 is equal to 0, see here in the diagram, I1 plus I3, I1 is equal to I2 plus I3. Okay, so here I1 is equal to I2 plus I3. So substituting into the first KVL equation, we get as minus 50 volt plus I2 plus I3. That is I1. I will replace this I1 by I2 plus I3. So here we will get I2 plus I3 into 10 ohm plus I2 into 8 ohm. Then 8 I2 is equal to 0. Or 18 I2 plus 10 I3 is equal to 50 volt. So, but from the second KVL equation, I2 is equal to 1.25 I3. So substitute this, the value of I2 in the first KVL equation, and we will get at 1.25 I3 into 18 ohm plus 10 I3 is equal to 50 volts. Or I3 is equal to sorry, I3 common, we can take the I3 common, or otherwise by solving this 18 into 1.25, it becomes 25.5 I3 plus 10 I3 is equal to 50 volt. So add it, you will get 32.5 I3 is equal to 50 volt. And from this we will get the value of I3 is equal to 50 upon 32.5, and that is 1.538 amperes. So we got the value of I3. Now once we got the value of I3, put this value in this equation, I2 is equal to 1.25 I3, and we'll get the value of I2 also. The value of I2 is equal to 1.923 amperes. Now remaining value is of I1. So we have this equation, I1 is equal to I2 plus I3. So substitute the value of I2 and I3 here, and we'll get I1 value as 3.461 amperes. So here we got all the values of the currents. Now what the remaining, we have to find out the voltage drop across each resistor, and voltage drop across each resistor is nothing but the current flowing through that resistor or through that particular branch into value of that resistor. So the current or voltage drop across 10 ohm resistance is I1 into 10 or 10 I1, and I1 value we have already find it out. So that is, will after substituting that, we'll get 3.461 into 10, that is 34.61 volt. Similarly, voltage drop across 8 ohm resistance is 8 I2, and that is 15.38 volt. Voltage drop across 6 ohm resistor is 6 I3 and equal to 9.23 volt. Similarly, voltage drop across 4 ohm resistance is 4 into I3, that is 6.15 volt. So in this way, we got all the values of current flowing through the all the branches of the circuit given, and also the voltage drop across each element. And hence, in this way, we have determined these values, and means what we have just analyzed is this simple circuit. Thank you. Thank you very much. Next time we'll see the more examples on this topic. Goodbye.